Welcome everyone. In this lesson, we'll learn how to solve one of the most common and interesting interview problems, finding the longest substring without repeating characters. We'll walk through the problem step by step, understand why it's so popular in interviews, and then write an optimized JavaScript solution that's clean, efficient, and easy to remember. By the end of this video, you'll not only understand how it works, but also why it works. Let's start by understanding what the problem is asking for. Given a string, we need to find the length of the longest substring where no characters repeat. Now, the key word here is substring, which means a continuous sequence of characters, not just any random collection. For example, let's take the string ABCABCBB. The longest substring without repeating characters is ABC, and its length is 3. Whenever we encounter a duplicate, we'll have to adjust our window, meaning we move our pointers to maintain only unique characters. In short, we're looking for the longest stretch of letters that are all different, and we'll need a smart way to keep track of that as we scan the string. This problem is a must-know for interviews, especially at companies like Google, Amazon, and Microsoft. It's a favorite because it tests how well you can manage dynamic data and optimize your thinking. It combines several key computer science ideas, like hash maps, two-pointers, and real-time tracking. And it's also one of those problems where the difference between brute force and optimized thinking really stands out. In brute force, we waste time checking every substring. But with optimization, we can turn a slow cubic solution into a lightning-fast linear one. Remember this, optimization isn't about magic, it's about doing more with less. Let's first understand the brute force approach. This is how most people would start if they didn't think about efficiency. Here's the idea: start at each character in the string. From there, generate every possible substring that follows. For each substring, check if it contains duplicate characters. Finally, track which substring had the maximum length without repeats. Sounds simple, right? But here's the catch: this approach is extremely slow. It has a time complexity of O of n cubed because we're generating and checking every combination. For small inputs, it might work. But for long strings, this method will crawl. For example, with ABCABCBB, you'll be checking things like A, then AB, then ABC, then ABCA, which already breaks the rule. So yes, it works, but it's not practical. Now let's move to the optimized approach, the sliding window technique. This is where things get elegant. Instead of checking every substring, we'll use two pointers, left and right, that form a moving window over our string. The window expands as long as we see unique characters. But if we find a duplicate, we shrink the window from the left until the duplicate is gone. Here's the three-step process. First, we track characters using a set or a map. Second, we expand the window by moving the right pointer and adding new characters. Third, if we hit a duplicate, we shrink the window by moving the left pointer until we're back to unique characters. This method ensures that each character is visited at most twice, once when added and once when removed, making it linear in time. A massive improvement from O of n cubed to O of n. Let's now look at the optimized code in JavaScript and understand what's happening step by step. We start with a function called lengthOfLongestSubstring that takes a string input, which we'll call s. Inside the function, we declare three variables. Left is set to 0, it will represent the start of our sliding window. maxLen is also 0, it will store the maximum length of unique substrings we find. Then we create a set called scene, which will help us track the characters currently inside the window. Now we begin a for loop with right starting from 0 and running until the end of the string. At each step, we check if the character at s, right, already exists inside our set. If it does, that means we found a duplicate, so we start removing characters from the left side using seam.delete s left, and we move left forward until the duplicate is gone. Once we've cleared duplicates, we add the current character into the set using seam.add s right. Next, we calculate the current window size using right minus left plus 1, and update maxLen with the larger of the two values, using math.max. After the loop finishes, we return maxLen, which gives us the length of the longest substring without repeating characters. This entire approach works in O of n time, since each character is processed only twice. Let's break this code down into its moving parts. The left pointer marks the start of the current valid substring. The right pointer keeps exploring new characters as it moves forward. The scene set holds only the unique characters that are currently inside our sliding window. And maxLen stores the longest valid substring found so far. Now, let's focus on what happens when a duplicate appears. Step 1. Detect the duplicate character. The while loop checks if the character at the right pointer already exists in our set. Step 2. Remove from the left. We delete the leftmost character from the set and move the left pointer ahead by 1. Step 3. Continue until unique. We keep doing this until the window contains only unique characters again. Finally, step 4. Update the maximum length. We calculate the current window size and update maxLen if it's the largest one seen so far. This logic ensures we always have a clean, unique substring window at every step. Alright, let's apply this logic with an example. Our input is the string ABCABCBB. Step 1. Start with a. The window is a, length is 1. Step 2. Expand to AB, length is 2. Step 3. Expand again to ABC, length is 3. Step 4. Now we hit a duplicate a. We shrink the window by moving the left pointer. The new window becomes BCA. Step 5. We continue sliding and updating. By the end, the longest substring we find is ABC, with a length of 3. Let's look at other quick test cases. If the input is BBBBB, all characters repeat, so the output is 1. For PWWKEW, the result is 3, with substring WKE. And for DVDF, the result is also 3, with substring VDF. This walkthrough shows how our sliding window adjusts automatically to handle any scenario. Let's wrap this up with a few key lessons. First, the sliding window technique is your go-to tool for substring and subarray problems where you need to handle continuous sequences. Second, optimization matters. We improved the time complexity from O of n cubed to O of n by using smart pointer management. Third, understand the space-time trade-off. We use a set, which takes O of n space, but that's what enables our solution to run in linear time. Now that you've mastered this problem, try related ones, like the longest substring with k distinct characters, the minimum window substring, or finding permutations within a string. And always remember, good code doesn't just work fast, it thinks efficiently.